So our next speaker, Joe Gratz, is a leading expert in AI-driven sports analytics. He specializes in computer vision and automation in ice hockey. Directing a team at a research team at the University of Waterloo, he focuses on advancing AI methods for analyzing player and puck movement from broadcast video. As Director of Intelligence at Stathletes, he also bridges academia and industry, delivering new insights and decision-making tools that are shaping the future of sports analytics. Still getting set up here, so we'll give him a second.
Thank you.
But I'm excited. I'm excited to hear from Joe about hockey.
Cool. Nice. Thank you. Give me 1 minute. I'll get set up here. Good. Okay. Good afternoon, everyone. So before diving in, I'd like to take a moment to thank the NESSIS organizers, Scott and Mark, and everyone else who's putting their time and effort into this, for making this event possible. It's an honor to be here at Harvard representing Stathletes, and I'm incredibly grateful for the opportunity for our analytics community to connect, and to share ideas, and to continue pushing the field forward. The topic of our presentation today is the impact of skating speed and style with tracking data by Jeff Gorey and Joe Gratz. So, let's start at the beginning with the data set that we used. So our data set consists of 280 AHL games from last season, and each game has approximately 105,000, around 100,000 puck positions and approaching 1 million player positions per game. So it's a lot of data. All of the data was collected using only broadcast footage and team rosters. So team rosters, you can imagine every team has potentially between number 1 and number 99, but if we narrow that down to 20 or 21, it makes the potential pool of numbers that we're pulling from much smaller and a little bit easier to detect. So tracking demo, typical broadcast usually runs 2 to 2.5 hours. Actual gameplay in a hockey game is 60 minutes, 3 20-minute periods. So we split the video into frames that look like this, raw video frames. And we end up with a few 100,000 of these at 30 frames per second. So a few 100,000 of these, not all of them are gameplay, many of them aren't. So I'll get into that in a minute about how we kind of get rid of things that we don't want, stoppages, commercials, things along those lines. So does anybody know what that green rectangle is? Any ideas? Anybody who likes hockey? Yes, up here. Yes, it's the hockey. Yes, good. Okay, great. So you guys do know a little something about hockey. That's fantastic. So yes, here we have various detection algorithms that are detection models that detect where the players are, who the players are. You can see they have numbers there, and where the puck is in this 2D frame. So we don't know where it is in 3D space yet. We just know where they are on this 2D image. So it's about a 1280 by 720 image. It's HD. The puck is maybe, 800x, maybe 650y, somewhere in that range, which is great to know as a starting point. But what we really want to know is this, where the players in the puck are in 3D space or on ice, where they are in the ice itself. So you can see here we use a process called homography, which some of you may be familiar with, to map where they are in the 2D image to where they are on the ice itself. So various models that we used for this, camera shot selection. So when I say shot selection, I don't mean like hockey shot, I mean like camera shot. So we remove commercial stoppages, crowd shots, things like that. This is the first step in all of this. Player detection, puck tracking, using a multi-object model called bot sort, jersey number detection and recognition, game clock OCR, so we know when something happens in a game image, how that corresponds to when it's happening in the game, and then rig features, so that segmentation and several models for homography. All of these per frame detections can be noisy. So we use a Kalman filter to help us integrate over time stable trajectories. We also interpolate short gaps, so if a player were to go behind other players, or the puck were to go behind players, we interpolate those small gaps. We suppress outliers. And as previously mentioned, we end up with somewhere in the range of 1 million of these data rows per game. So it's a whole bunch of data. This is less than a second worth of data, frame number, period, game clock, player, puck, which team the player's on, and the location within 3D space that that player is. So quick little story. For those of you who've ever seen hockey, and for those of you who haven't, this is what a hockey puck looks like. It's really small, and it moves really fast. This is an actual game puck from a game in St. Louis. They hit it really hard. And sometimes on a broadcast, it can look so tiny and fast, it looks basically just like a smudge that teleports. So this is one of the reasons why it's difficult to track on broadcast video. There's always going to be a trade-off. If you tune the detector to catch more pucks, you get more false positives. If you tune it to be more strict, then you miss things like cross-ice passes and one-timers, where it's hit really hard. So about a year ago, we were working on data for an NHL client, and we had a rink where our model was absolutely certain that a little part of the center ice logo was the puck. So on zone entries and exits through the neutral zone, our system thought the puck got passed to a random logo fragment, even when the puck was clearly being carried the entire time. So how did we fix it? So first, since this is supervised learning, for any of you who are familiar with this idea, a great way to fix this is by going back and augmenting the labeled training set with hard negatives from that specific rink, which allowed the model to learn that that shape within the logo is not the puck. So that solved the logo for that specific rink, but other phantom pucks are still going to pop up. There's glare, scratches on the ice, tape on player's sticks, even compression halos from the broadcast feed. So that's where temporal logic steps in to save us. We've got Kalman to stabilize trajectories. There's appearance velocity gating to reject things that don't move like the puck. And, as I'll get to in our next slide, a Savitsky-Golay filter that kills micro jitter without flattening real speed bursts. So the lesson is, single frame detectors aren't enough. You need temporal coherence to turn pixels into believable hockey. Oh, clicker. Sorry, try that way. There we go. Okay, great. Okay, Savitsky-Golay. Even with Kalman, derivatives can be touchy. So a Savitsky-Golay filter, which for those of you who don't know, it's a short window polynomial least squares smoother. It reduces noise while preserving curve shape, so things like speed, acceleration, and burst stay truthful. There's a polynomial order, and that controls how flexible the fitted curve can be, how many times it's allowed to change direction. In our case, we chose a cubic polynomial, which balanced smoothness with responsiveness. And then there's also a window size. So the window size is how many frames before and after the current frame it's allowed to look. You can go very small or you can go very large. We chose plus or minus 5 frames. We found that to be a good trade-off. It's about a third of a second. So we found that to be kind of a good trade-off between capturing quick movements without over-smoothing. So this setup did a really good job of reducing noise and still keeping the important features of the data. We've got some animated charts later on that will really kind of bring some of this to life, and you can see how the actual detections look on an ice hockey rink. Okay, so sorry, give me 1 sec. I'm going to take a quick drink of water. Okay, so from here we compute, I would say, some more somewhat basic metrics. So we have distance traveled. So distance traveled is miles that somebody would skate in a game, ice time, energy, power consumption, and speed bursts. So with speed bursts, we have sustain on the left, speed on the right. You can imagine with something like a speed burst, if a player can get to a certain point on the ice before another player, they're probably going to be pretty good at hockey. Certainly really useful for evaluation. Quick note regarding time on ice. Since it's a really common metric, you see it in almost every hockey box score. It's only a tiny slice of the story. So for example, I could skate 20 minutes for the Bruins, which is purely hypothetical because I couldn't actually do that. And Charlie McAvoy could also skate 20 minutes, who's a tremendous defender for the Bruins. And on paper, that time on ice would look exactly the same. Excuse me. But the realities of what took place in that game would be completely different. So that's all to say, time on ice is not a very useful metric in describing what really happens in a hockey game. Okay, so one of the ways that we can quantify space is with Voronoi tessellations. So Voronoi tessellations is each defender's first region. It's binary, so basically meaning whether that defender can reach that area of the ice before somebody else or not. On the left, that's what we have. Each of those defenders has a tessellation that they're occupying. And on the right, we have convex hull. So it's the smallest convex polygon containing all defenders. So you can imagine that can be, like this, or it can be a square, or a rectangle, or a triangle, with 2 defenders inside the triangle and 3 on the outside. It's a good way to kind of measure the way that the defense is set up. Another metric that we have is gap and gap closure. So gap, typically in ice hockey, gap is the closest distance from the defender to the offensive player. It's kind of chest to chest, basically, is how it's measured. The way that we decided to measure it, because we found it to be a more accurate representation of what really happens on the ice, is from the closest defender to the puck. So in this case, the gap is 18 feet. Then we have gap closure, which is whether that the rate of change in the gap, whether it's closing or widening, somebody's getting closer to the puck or farther away. In this case, we've got a gap closure of plus 2 feet per second. So that means that the defender is kind of just slowly encroaching on the puck at 2 feet per second, not very quickly. Okay, so imagine I'm a defenseman and I play in the NHL or the AHL. Again, purely hypothetical, and I'm patrolling a certain zone, and I'm yelling to my line mate, "Yo, bro, stay in your own tessellation." Good, I got some laughs out of that. That's good. Because they probably wouldn't really say that, FYI. And we want to measure kind of the way that I'm patrolling that area. And how big that area is. So a roaming metric tells us how much area I'm covering, and the stretch metric tells us the type of shape that that's in. So it's either going to be more lane-like or more elliptical, or it's going to be more circular. So in this case, we have 2 different players that have approximately the same roaming value, about 5 feet, but the stretch value is very different. On the right, we have a player with a much more circular stretch value. And on the left, we have one that's much more elliptical or lane-like at 59%. So this kind of tells us, we use these metrics in later formulas to kind of tell us more about what's happening on the rink. So after some trial and error, we found eigenvalues to be a simple, robust way to capture these values. It was kind of perfect for what we were trying to do here. Beyond Voronoi. Okay, so I talked about Voronoi tessellations before. Now we're getting into region control. So Voronoi tessellations are binary, whether that player can reach that area or not. Region control is more probabilistic. So what are the chances of this player reaching a certain area in the ice before another player? It also factors in speed, how quickly the player is moving, and what direction they're moving in. So you can see there's some white areas there, which are basically 50-50. As you can imagine, who can hit a certain 50-50 area before another player is going to matter a lot when it comes to winning a hockey game. Okay, right here, this is a really good representation of how important speed is. So over on the right, these three, I should say, too, are all the only difference. The players are all in the exact same position in all three of these, and the puck is in the same position. The only difference is that guy kind of in the middle there, the orange attacker, is moving. We experimented with different rates of speed for that player. So here he's moving more slowly at 11 feet per second. This was the actual recorded speed, 17 feet per second. We tinkered with what it would look like if he was moving more quickly at 25 feet per second. So as you can see, that region that this player controls gets much larger as he moves more quickly. At 25 feet per second, he controls a much bigger region on the ice. Sorry, give me 1 sec, I'll take another drink. Okay, now passing. So we trained a shallow neural network on labeled event data fused with tracking data to predict pass completion probability from the puck carrier to candidate receivers. In this visual, you see over here the expected the expected percentage of completion, pass percentage or pass completion percentage to this receiver over here to be about 92%. And up there to that other one, the guy we were looking at with the region control in the previous frame to be about 18%. So if you looked at just this slide, you would think, okay, the right decision without a doubt is to pass to this guy right here, that 92% pass. But, spoiler alert, the Stanley Cup has never been lifted through passes alone. You still need a shot to actually score. So as it turns out, even though it looks like that's the optimal decision, it's actually not in this case. And we'll get more to that in a couple of slides. Visualizing pass completion percentage. Here, we're just kind of tinkering with the location of the puck. It's kind of in different places around here. All the players are in the same spot, but you can see how it really lights up, the optimal receiver to pass the puck to based on where the puck is. Just shows the importance of the puck. Okay, so going back to what I was talking about a couple slides ago, now we're into expected possession value. So what is the value of the possession for the entire time that the team has the puck? So we're taking into account passing, carrying, shooting, and you can see here the expected possession value we're building on the previous models that we talked about before is actually only 1.8% to this receiver, the one with the 92% pass completion, well, it's 3.1% to this guy in the slot. So as it turns out, the optimal action value, despite it being a much more difficult pass right there, is actually much higher to that guy. It's 3.1% versus 1.8%. Just for reference, the optimal action value of all professional hockey is calculated to be around 1.5% on average. So neither of those decisions is necessarily a bad one. It's just one is much better than the other. Okay, now we're building one more step on top of that, optimal action value. What we're looking at here is the value of the optimal action the puck carrier can take at any particular time. At any particular time, they have the option of passing, carrying, or shooting. Now, oftentimes, more often than not, they're going to be carrying because it's, they're skating around with the puck as the puck handler, but these windows open up every once in a while when they could shoot, when they could pass. The first part of that formula, it's kind of set up that way because there's multiple receivers that the passer could pass to, and then carrying and shooting are factored in as well. And we'll have some videos coming up later on that show this, that highlight this in actual game footage. Here, we're just kind of summing everything up, all the different metrics that go into the models that we created, and how they look all together. A little bit more on this later. We also trained a gradient boosting model on offensive zone possession windows to explore the relationship between defensive attributes and scoring chances. So here, what this is telling us, optimal action value, it's kind of hard to see, and there's a lot going on with these, but we've got distance traveled, haul area, region controlled, calories burned, gap closure, some other things there, but the very top one is optimal action value, which is much higher than all the rest. So it kind of is no surprise that it would carry the most weight because it's taking a whole bunch of different things into account. But for us, this just kind of told us that we were on the right track with our optimal action value model because it correlates very highly to scoring chance quality, which is XG. Quality versus quantity, I'll go through these slides because I know I want to run out of time here. Quality versus quantity here. Gap appears to impact shot volume a lot more than shot value is what this is telling us. So here we've got the same metrics on the left as we do on the right, but they're how high up they are within the ranking changes on the left and right. So you can see we've got quality here and quantity here, how many shots I take, how high quality are the shots. Gap is much higher on the right. So again, gap is the distance between the closest defender to the puck. So you can imagine if somebody kind of like goes in closer towards, the puck as a defender, that's going to impact the amount of shots that somebody's going to take. Okay, gap closure, highest impact. Here on the right, we've got gap closure and then stretch score as well. So, which is measuring the stretch score on the right. So it's just different ways of looking at some of the metrics that we attained earlier on and how they correlate to XG, basically expected goals. Okay, so now I'm kind of setting up the next slides. In this situation, you can see the defense kind of cheated there. So we've got 4 defenders in the top frame, 4 defenders all kind of going towards this one puck handler, which probably isn't the best idea in most situations, and it certainly wasn't here, but it's what they did, so what can you say? Interestingly, which worked out really great, our model detected the correct action and in this situation, and so did the player. So this player, who I think is probably pretty good because he saw this and all the defenders are kind of like rushing him, so they must think that he's capable of some really cool things. He sees this guy over here where the arrow is pointed to as the correct receiver to pass to, and he does hit him, and then he hits this receiver who has it, now sees this guy as being open as well. And you can see we've got a defender kind of hanging, I think he's maybe a rebound by the coach, or maybe he already did since this game happened, because I don't know what he's doing. He's just hanging out there, not really having much effect on the play at all. So you'll see the whole thing play out here, and I'll just let that play. Bless you. Okay, so here, that's the entire play that we saw those screenshots for. The defenders are going to cheat. It's doing it over and over. The defenders cheat towards that guy. He finds the right receiver, and then it goes back. They didn't score on this play, but whether or not they actually scored is less important than whether they made the right decision. Over time, if they make the right decision often enough, they're going to score more than the other team. So there's a lot of stuff happening down here. Optimal action value, pass value heat map is what that is, and all these things lighting up here on the fourth one, the fourth visual is region control. So these are the areas of the ice that each team is controlling. The defense blue, the offense red. You can kind of see how it changes frame by frame, and then we've got the puck speed over there. It moves when it moves more quickly. It's kind of lit up as bright red. You know, so you can, it's funny, like even without seeing the players, with just seeing the puck, you know exactly when it's passed and kind of, you know, what happens based on how quickly it's being, you know, sent across the ice. Zone entry. So final thing that we'll talk about today is zone entry. So we did from some similar things to what we were doing before, except these are based on zone entries, and 5-on-5 versus 5-on-4. For any of you who don't know hockey, 5-on-4 is a power play. So it just means there's going to be one less player on the ice because of a penalty. And so this is exploring some differences between also a gradient boosting model on zone entry windows to explore the relationship between defensive attributes and scoring chances. And finally, almost finally, this is kind of setting up the next slide that we're going to be, the final slide that we have, which is just putting a lot of this stuff together. You can see here, we've got a player who's about to cross the blue line, so he's coming in to his offensive zone, and he's coming in at a certain angle, which is 15 degrees from center. There's a certain gap, and the defender, that is, there's going to be a certain gap for the defender. The gap closure rate is actually negative here, negative 7 feet per second. What happens to mean in this case is that the puck is moving away from the player, essentially. Okay. This is similar to the other video that we had, but same kind of thing. You can see optimal action value. I don't know if I pointed that out very clearly, excuse me, in the other slide that we had that was similar to this. But optimal action value spikes when something really interesting should happen. Not necessarily does happen, but the players should be making a certain decision. Passing, shooting, sometimes they do, sometimes they don't, but this is what our model is calculating. You can see the puck also here, how elongated the arrow gets because it's moving very quickly across the ice in those situations. This is kind of loop again. It does take a few viewings to really see what's happening here. Okay. So simply put, we used one of our data sets at Stathletes, hockey tracking data attained from broadcast video to better understand the optimal hockey play in different situations. And I'd be happy to take any questions that you might have.
We got time. I'm told the cubes are back. We got time for one or two questions, quick ones if we got them. Any questions? Over here first. I'll come back. I don't know if I should be throwing these or not. I'm going to try.
Yeah, so in this example on the zone entry here, you get like a spike on the optimal action value when the guy doesn't have the puck. So is there like off puck components to the like composite action value that guy was supposed to do?
Yeah, predicting who will get to the puck first.
Okay, gotcha.
Good question.
And then over here there was one.
I didn't look trustworthy enough to throw it to you. So on this example here, am I understanding it correctly that it would tell you the optimal value of passing it, but it never tells you when it's just optimal to shoot it?
They're kind of, it's on here, right? They're kind of all in one, so it's essentially all part of the same. Like if the optimal value spikes, it means we can kind of like pull that out and know what the optimal action would be. Yeah.
So that left arrow is changing between pass, carry, and shoot. It's just not showing us what it's doing.
Oh, okay.
All right. Thanks, Joe.
Of course.
It was great.
Thank you.
Let's give a hand for Joe Gratz.